This video is focused on interpolation or smoothing methods. We will be starting with a disk mesh. Please watch our quick tutorial called Intro to Projection to learn the steps to project a disk in detail. If you would like to build the same disk that we are using in this first example, here are the commands to build the disk.
Now, there are two problems with this mesh. One is this is 90 degrees right here. This is known sometimes as an irregular node. And we have a 90-degree angle here, and that would mean that each of these is 135 degrees. We can do better. The second issue is the elements here are larger than the elements in here, and we'd like to have them about the same size throughout the entire disk. So I'm going to use what we call the block boundary interface. If I were to use one of my smoothing algorithms on this right now, these would be considered boundary conditions. They would not be modified because they are not connected. These nodes would not be allowed to move. Let's do that first so we can see what we get without the block boundary command. So I'm going to use uniform. And I'll select these three faces, F1, but then I can choose another region, and that's this one here. Hit F1, and another region right here, F1. And I'll put in, let's say, 300 iterations this time. Execute and quit. You'll see here, this is awful. These nodes were not allowed to move on this edge, but everything else wanted to move in this direction outward. So we have this crunching up that takes place here. Now what we're going to do is glue them together. That is, we're going to tell TrueGrid this edge and this edge are to be treated as one edge.
For each block boundary, there is a command that defines the master and a second that defines the slave. Here, we are typing the commands into the text box and using F1 to insert the selected region, followed by the block boundary number. There should be 2 commands for each of the 4 block boundaries we are forming. If you prefer, you can use the dialog box to build your commands by selecting BB in the interface menu.
Then I tell it to remake the mesh by telling it to draw. And look at the remarkable improvement. And I dare say there's no better mesh for a disk than this method. We have only 4 irregular nodes.
And the 3 elements that share those nodes share the 360 degrees as evenly as possible. But let's measure just to be sure. Let's zoom in and use the SUBANG tool to examine the quality of the new angles located at the nodes.
From here to here, F7 to here, F7. 119.5 degrees. Ideally, it should be 120. Close enough.
For the next part of this lesson, we're going to use the model that we built in the nodal distribution lesson that already has nodal constraints on all 4 edges of the mesh that has been projected onto the cylinder.
I want to show you some of the more sophisticated interpolation algorithms. These are going to be across the entire mesh. The edges are going to be the boundary conditions for the interpolation, and they will not be changed. So I'm going to start out with linear. This is the default. It's the fastest, but it doesn't use much information from the boundary to interpolate the interior nodes. Sometimes the mesh lines will go outside the boundary. Now, I don't know that I've made it bad enough to make that happen. I'll frame in a little bit and see if I can find any problems like that. No, it doesn't look like it went outside, but this method is quite capable in extreme cases of having the interior nodes go outside the boundary. No, I don't see any of that in this example, but it's not a good mesh. What it's doing is for every node, it follows the line to the boundary. So it has 4 boundary nodes it looks at, plus the 4 corners, and it does an interpolation based on those 8 points. Transfinite, it's a more complicated method of interpolation. So this is a little better. The elements are reasonably shaped, but they're still constrained. I mean, the first element has to have a length of this size. So what can you do? You got to have an element that big because the boundary dictates it. But that takes up more CPU. It's more complicated. It looks at every point on the boundary when it goes to interpolate every interior node. Now, these are both algebraic methods, and it's a one-pass algorithm. It's not iterative. We have some iterative methods as well. So, for example, I'll show you the relax command. This is solving a system of partial differential equations, and you tell it how many iterations to do, and then you give it also a minimum change. Now, if that minimum change is met, in other words, in one iteration, all of the interior nodes moved only a small amount less than the minimum, it stops before it iterates 100 times. You could use 0, which means it's going to do all 100 iterations, and that's what I'm going to do. Now, the interpolation parameter, it's hardly ever anything but 1. Sometimes I'll use a number smaller than 1 because I want to dampen its effect, but never greater than 1. I'll just use 1 this time and redraw. Now, equipotential relaxation is trying to make the elements in the middle equal in size. So when you have extreme boundaries like this, they radically change very early on so that it gives you a decent mesh on the inside. And that's what you're seeing happen with this.
This next interpolation or smoothing command is intended primarily for computational fluid dynamics. It was developed by 2 mathematicians at Stanford University, Thomas and Middlecoff. It's the TME command. It results in a mesh that has more element density as the mesh reaches the boundary. In CFD modeling, it's often used in conjunction with various edge nodal distribution commands to achieve the desired effect.
And you tell it how many iterations to do, and then you give it also a minimum change. I'll do 100 iterations and a minimum change of 0. But it's going to try to give us near orthogonality near the boundaries, which is going to be pretty tough for this problem. Oops, step size 1. Radically different from the others that we've looked at. And if we look at the boundaries, they're not 90 degrees. They're not bad, but just different. And this would be used more when you've got boundary conditions like we have here, not extreme like this, but where you have a concentration in certain areas, in large elements in other areas. This will carry through that concentration all the way through the mesh. See, TrueGrid is good for both fluids and structures. Now, there's one other smoothing algorithm I want to show you. And it's the one I prefer. But the problem is it's slow. It takes up a lot of CPU time. It's a derivative of relax, but we call it uniform. And it has an advantage over relax in that when you have curvature, it handles the curvature better. The curvature can do some distortion. So I'll apply this command using the uniform method instead. I'll do 200 iterations since it converges very slowly. And a 0, step size of 1. In a problem like this, it's probably no better than relax. But there are many places where this is very useful.
This next set of interpolation command examples starts with the model from the lesson called Curve Attach Commands.
Now you might ask the question, why would we want to reinterpolate a face? I'm thinking of reinterpolating this face. Now that's these 6 faces, and each one of them is being interpolated right now independently. For this region here, it uses these 4 edges to interpolate the interior. and the same for each one of these 6. But if I apply an interpolation across multiple blocks, it will eliminate the freedom of, let's say, this edge right here. It'll no longer have any degrees of freedom. It'll be interpolated right along with every other node on the interior. Well, why would you ever want to do that? Well, here's why. Suppose you're building your mesh, and you need a partition right here to capture some feature. Maybe there's a curve, and you need that mesh line to follow that curve. But on this side, we don't need that partition. Well, the problem is that that partition goes all the way through. You're stuck with it. You've got to have a partition here. But you can apply a multi-block interpolation. So essentially, this is no longer a partition. You've taken away its degrees of freedom. And the one I might use is transfinite. Of course, there's not a whole lot that's changed here. But now remember, we also studied the different ways of controlling how the nodes are distributed along the edges. And I'm going to choose this edge. It's going to be RES at F1. And this is an edge in the K direction. And I want it equally spaced. Why? Well, if you look closely, these elements are much bigger than these. I want it to be equally spaced. So you see they're now equally spaced. And now you look at this block and you think it's not 6 different blocks, it's just one. We've essentially erased the block structure of this region of the mesh by using interpolation. And I get a much smoother mesh. I can't have that smoother mesh here because I'm going to have to place it along a curve. But this side can be freely interpolated.